Hey everybody, welcome back to the continuing OpenPnP adventures. Today we're going to be talking a little bit about feeders. What I've got here on the workbench is a partially open Siemens Schultz feeder, and this is a somewhat rare 3-lane 8mm tape feeder. There are a handful, or 10 or however many people in the world that are using these surplus Siemens Schultz feeders on their OpenPnP builds. And these feeders came out of industrial Siemens pick-and-place machines that were built probably back in the late 90s, early 2000s. I've got date codes on these particular units that range from the year 2000 up to the year 2006. And I think at this point they are being phased out in favor of more modern equipment that runs faster, handles smaller components more accurately, all that kind of stuff. As a consequence, these feeders are coming up available in surplus, either through SMT resellers or just random eBay listings. I would guess in a lot of cases, sometimes the overall machine fails, so people just part them out and they sell off the feeders. These 3x8s are a little pricey. You can get the 2x8 certainly for a lot less money, but the real benefit of these things is that they take up a little bit less space, so you can fit more components in your machine. If you've got a space-constrained machine, that's a benefit. We don't particularly have a space-constrained machine, but I ran into these things before I found a big lot of 2x8s, and I thought it would be cool to give back as much as I could to the community and get these things working, because currently there isn't really support for these particular feeders in the controller that Bill Ruckman developed. So Bill makes two different versions of this board. This is the one that breaks out to 20 individual 4-pin connectors, each one going to an individual feeder. He makes another version of that board which has a 96-pin connector on it that connects to a piece of Siemens equipment. If you've seen videos of actual Siplace machines, there's this huge panel on the back that has all the connectors that the feeders have on them and allows them to be plugged in when they're mounted up on the machine. His board can connect to the internal connector on that PC board and provide access for OpenPnP. This version is probably the one that people who are just buying feeders but don't have the rest of the machine will use. Each one of these connectors has a ground plus 30 volts and then transmit and receive. The Siemens feeders speak async serial, just like a lot of other devices in the world, but it's not electrically compatible. It is 0 to 30 volts. So his board has level conversion on the back, just a bunch of transistors. Ordinarily, every feeder comes with one of these LEMO connectors on it. It's a 7-pin, very robust, expensive connector. And you can get Chinese clones of these things that cost maybe $5 or $6 instead of the 50 to 60 or whatever these things actually cost if you buy the real LEMO versions. But what a lot of people are doing is disconnecting these internally, because inside the unit, they just have these 4-pin, 0.1 inch spaced headers. They will disconnect where that LEMO connector normally plugged in, and then just run some other type of 4-pin connector that suits their particular build. So let's get in a little bit to my test setup here. See, I've got this thing arranged on a piece of aluminum extrusion. I've set up a temporary way to hold the reels in the back here, and I do have this feeder set up with 3 reels of just some random 0603 components that I happen to have lying around. I'll go through the different components in the path that they follow through the machine. This won't be a full teardown, but you can see I've got the side panels off, so you do actually get to see some of the insides, and it really functions basically the same way that the 2x8s do, but it's a mechanical repackaging to fit 3 of them inside the unit. So let's start at the back here. On these feeders, you get a triple 7-segment display, and you get 3 buttons. So the blue button allows you to choose your lane. You push that, and the decimal point indicator on the 7-segment display shows you which lane is currently selected. So now currently lane 1 is selected. The green button actually executes a feed. You can hear that clicking away in the background. And the yellow button runs the tape foil take-up motor. So if I error it out by releasing the tape, as you can see now it's floating here in midair, we get an FO1 error, which means foil error on lane 1. If I run that motor, it takes it up, the error clears because the little lever here, which we'll look at in a moment, is actuated. To change the pitch on a given lane, you hold the green button down until the number starts blinking, and then you tap the yellow so you can see it can be 8, 2, or 4. And if you want to do that on another lane, you hit the blue button, switches to the next lane, hold the green button down again. You can see it flashes, but we won't change it in that case. Below the display here on the back, got these 3 compartment doors. These are actually where the spent foil, the cover tape, goes. It just basically curls up inside these things, and you have to open them up periodically and dump it out. You can see on the underside here, I've got my temporary reel holder. The individual tapes come in from the rear, and this piece of aluminum here is actually a rectangular tube, essentially, with 3 lanes inside of it. The tapes follow this path, go up this ramp, and then they eventually pop out up here. So just to see that again from this different angle, they come from the back of the machine, come up this ramp, and then each tape individually pops out here. This little tiny area here out of this huge feeder, which is something like 20 inches long and 4 inches tall, this little section here is really the only part that the OpenPnP nozzles will interact with. So each lane has this arrangement where there's a shutter and this little ramped piece which helps peel off the cover foil, and that's all held down with these spring clips. So you release a spring clip, the first part that flips out of the way is the shutter, and this is actuated by a solenoid inside the unit when you instruct it to open the shutter. So you can see this part slides up and down. At the very end of this, there's a little bent piece of sheet metal that actually holds the component in place that's about to be picked. That way it can't get bounced out if there's machine vibrations or any other situations. Underneath that, you'll see this ramped piece here. The cover tape is basically peeled off right up to that point, and the component that's about to be picked is available. The rest of them are protected. So the component that's about to be picked is up here. The tape is peeled all the way back to there. The underside of the shutter has a flat bottom on it, so these parts can't go anywhere, and the shutter is holding the final part. So when it's all assembled, the shutter is closed now. The part that's about to be picked is right where the tweezers are. I'm going to open the shutter. Shutter's open. Now the nozzle can come in and pick up that part. You come in, the shutter opens, the part would get picked, and then a feed would happen. Normally that part that's still there would be gone, the nozzle would have grabbed it, but the next part is then available. So it's all very quick. And this is true on every single one of these lanes. So here's the second lane moving, and the third lane. Now, the way the cover tape is dealt with, we talked about that ramped piece. The cover tape is peeled back, goes up that ramp, and then it's stretched all the way back to the rear of the unit here. And the next most important section that it goes through are these 3 levers. These levers are used with a combination of these opto sensors that are inside. And when the levers are up, basically the microcontroller detects that there's no tension on the tape, so it attempts to take it up. If it can't put tension on the tape within a certain amount of time, it'll error out. The tape travels over these levers and then down into these teeth down here. There's 2 sets of these little gear teeth that mesh together, and it grabs onto the cover tape and pulls it into those chambers that we saw earlier. So you'll see when I execute the feed on lane 1, you're going to see this lever bounce up in the air a little bit, and then this motor will run very briefly to take up the tension. So you can see that little bit of a bounce. If I use these levers back here, which release the tension, basically just lifts up one set of the teeth, you'll see that the tape tension will release. The motor runs to try to take up the the cover foil tape, but it errors out because it can't grab it. So you can see here now the tension is released on that cover foil. Just as a note, I think I have these cover foils routed incorrectly. I believe, since I checked the manual, I think they're supposed to go over this roller instead of under it, but for the purposes of showing this on the bench, I don't think it really matters. You can see that the lever is up in the air. That little opto sensor that's inside down here is registering that the lever's up and it can't take up the tension. But when I do the yellow button on the back, will manually run those teeth until it sees that lever go down. So now the tension is taken up and the error is cleared that we were seeing on the display back there. I have this other feeder unit taken apart. This isn't the one I was just actively using. So normally this whole side would be covered by a sheet metal plate, but these cables all hang out the bottom of the feeders essentially. Once you pulled the side plates off, you can see that the cables route up through this channel. They make their way up inside this aluminum and then they plug in to this connector here. So the cable you're looking for inside has green, yellow, white, and brown on it. On the underside of the feeder, there's a plate that you take off, and inside that compartment is the control board for the feeder. Unlike the 2x8s and some of the other feeders, all of the connections for the individual motors and sensors and all that stuff don't connect directly back to this board. There's a separate kind of mezzanine board, and this board is held in by 2 screws, but once you pop those out, you grab these 2 plastic pegs and you can pop this board out. This is a card edge connector that connects to that mezzanine board that you can see down in here. This board has the microcontroller, some motor drivers, some power supply circuitry on it. And the mezzanine board up here has the connections that go off to all the individual motors and sensors, and the card edge pokes down into that compartment that we saw earlier. So there are differences in the protocol for these 3-lane feeders versus the 2-lane feeders. How do we figure those out? A good way to start is to pop this board out and find out what this chip is. Now this is a bit of a dramatic reenactment. I've already done this. I can tell you what that chip is without peeling this particular label off. This is an Atmel AT8955, which is an 8051 microcontroller variant. These were very commonly used in the late 90s, probably mid to late 90s, early 2000s, for industrial control applications just like this. So it's interesting and it's very handy that this chip is socketed. The label tells us a little bit about the part number and the version of code that's on here, but there's a good chance we can actually read this code out. I typically don't like to use these with these surface mount versions of the sockets. These are better for the through-hole versions. This is a, you can see it's a very thin surface mount version, so I will use this tool, but I'll use it more like the other style. You can put the hook into the corner, just give it a little bit of gentle pressure, and then go to the opposite corner, get the hook in, and the chip pops right out. In the bad old days, you needed a million different adapters to be able to read and write different kinds of chips. And this particular one right here converts from the PLCC. So these PLCC chips mark pin 1 basically with this little dot, but they also have a flat corner, and that flat corner matches up with the socket. So you just carefully position it in the socket, you put it in there, and you wait for the crunch. Well, kind of more of a snap in this case, but flip the lever down and it's ready to read. And the first thing you have to do with any of this EEPROM programming software is tell it what kind of chip we have in the programmer, because it can't figure that out by itself. So we click Select IC, and you're presented with a huge table of manufacturers and individual chips, but thankfully we already know what we're looking for. We can just use the search function. So we're looking for an AT89C55, and this particular variant that's used in this version of the feeder is an WD. I think it's a slightly newer version of the chip. The other one I took apart was actually the older one. It was not the WD version, but this one is a WD. Select that. This area in the software here shows a dump of the memory location. We haven't read it out yet, so it's all Fs. You can see that's how it starts out. We're going to do device, read. This screen shows you a handy little reminder that you should use that adapter that we already set up. All we have to do is click read. Takes about a second. Close that out, and you can see now what was all FFs before has a bunch of code in it. And the 8051 reset vector is located at 0. So you can, if you look at the first couple bytes of the dump, if you see an O2 and then a couple of addresses, that's a good sign that this is valid code, because it basically, the first thing it will execute is this instruction, which is a jump to a memory location. So we're going to save this off as a hex file. And this is a slightly different version of the chip. We're going to save that hex. And I brought that hex file over into my Linux workstation, and we're going to use a tool called D52, which is a disassembler for 8051 code. And it's very simple to run. Basically, just takes a command line argument for the hex file. You run that, takes a pass through the file, and turns that bunch of binary data into readable assembler code. So reload that code here. This is what that code looks like. So all those hex digits we saw in the EEPROM programmer actually translate to instructions that the microcontroller executes. This is that same binary data, just in human readable form. So some of those bytes are opcodes, and there's arguments to them. And when you first run the disassembler and you have no labels, basically, you just get a bunch of instructions and random memory locations that it jumps around to. You have no idea what any of that stuff means. So you could be looking at this block of code here, for example. There's the only thing human readable in here are the opcodes. So you generally use what's called a control file with a disassembler, and that's what I've got open here in my Emacs window. Now this is a control file that Bill Ruckman, who developed the controller board, started, and he's done this disassembly process for the earlier 2x8 versions of the Siemens feeders. So we were able to start this project with a leg up from him, a huge leg up, because it's a big deal to start figuring this stuff out from scratch. But essentially it's like putting a puzzle together. You start out with what you can figure out or what you already know. So every microcontroller has known addresses for things like the UART controller and timers and stuff like that. You can define all that stuff with human readable labels in this control file and run the disassembler again, and then when it disassembles, it actually uses those labels you just assigned so that it looks sensible when you look at it. And you keep iterating on this process. For example, I have been going through the actual I/O pins on the controller, the GPIOs, and figuring out what they connect to. Like this one connects to a motor controller, and this one connects to I2C, and that kind of stuff. And we fill in the labels in here, and then when some chunk of code is actually, for example, setting bits to run a motor, you can start to make sense of that. The other most important stuff that Bill got a head start on was figuring out the UART decode sequence for the protocol. So he was able to find where the bytes are read in and parsed out, and the protocol structure is analyzed to figure out what commands get dispatched. So within a very short amount of time, he knew what commands this feeder could accept. And again, it's the same format packets that the 2x8s use, because they're all part of the same system, but the actual commands are a little bit different. So it means a lot to know that, you know, this thing responds to these 10 different commands. Through the use of external tools, actually exercise the feeder with those commands and see what happens. But you can also start to fill in and understand what they mean by looking through the code. So in the protocol, the commands are basically a single byte, and there's maybe 10 of them that it responds to. And some of these we have no idea what they do. There's clearly code in here to handle it, and it's our job to figure out what the heck those do. So for example, here's the part in the UART code where it processes out command 32, and we've got it labeled with a thing that says, hey, this is command 32, and it called out to some other random memory location, and we said, all right, that must be the command 32 handler. So we've labeled it command 32 handler. You can find that code here, and you can see that it does some stuff with the UART receive buffer. There's this lane variable that Bill found that it sets, and you can see that it dispatches to these 3 different functions depending on which lane is set in the serial protocol command. So if it's lane 2, it jumps here. If it's lane 3, it jumps there. And the lane 1 handler code, for example, is here for command 32, and we don't quite know what it does yet, but we can see that it does some stuff with the receive buffer, and then we've also figured out that there's this set of functions that save off settings to the EEPROM. So you can see that it sets some stuff and saves some things off to the EEPROM. So we have to put more work into figuring out exactly what it's doing and what that stuff means, but so you can start to make sense of this thing if you put the time into it. Meanwhile, we're also keeping a Google document that we're sharing, and for example, we found commands to dump out contents of the EEPROM. It's a 256 byte EEPROM. The feeder stores things into that EEPROM, or has some things already set in it, for example, serial numbers, and by applying just some patience and exercising the unit and comparing EEPROMs, before and after when you've done these things, you can start to discern what some of these locations mean. So for example, this is a map of the EEPROM for one of these feeders, and you can see that we figured out that these memory locations here mean the feeder pitch, or the feed pitch for particular lanes, and that the serial number for the unit has been programmed in. It's the same number that appears in a sticker on the side of the unit. So it's kind of cool that you can figure this stuff out, and it all makes sense. Then it'll be up to just writing some more Arduino code to make a driver essentially for this particular type of feeder versus the 2x8s. And that's the easy part. Once you figured it out, it's easy to sit down and write some code that does the thing that you already understand. So I'll be updating more progress on the project soon. We've got some exciting stuff going on in the vision department. We are working with some interesting coaxial illuminators to eliminate some problems that we've had with the ring lights, and hopefully we'll be actually picking and placing parts soon. So stay tuned.